Dudley. Thanks a lot. Dudley, how about some coffee? Good idea. You know, I never expected to get those ringworms. Why not? I suppose you never...
Teacher and student. Professor Simon Ostrach began his career in scientific research by solving critical engine problems that threatened the B-29 super bombers in the closing months of World War II. He worked 16 years with the National Aeronautics and Space Administration and its forerunner, the National Advisory Committee for Aeronautics, before joining the faculty of Case Institute of Technology. His work in thermal and fluid sciences has earned him an international reputation. Dudley McConnell will soon be Dr. Dudley McConnell. The successful experiment he's just completed is one of the final steps in over 3 years of advanced graduate study, financed by the National Aeronautics and Space Administration. Since 1957, McConnell has worked at one of NASA's largest research facilities, the Lewis Center in Cleveland, Ohio, birthplace of high-energy propulsion systems. Tonight's experiment has a history that began back in 1957. Simon Ostrach recalls those early years.
Well, at NASA, they organized a number of panels, and these panels were confronted with the important problems. One such problem was that we were going to have missiles and later on vehicles with people in them coming through the atmosphere. And as they came through the atmosphere, these objects would become enormously hot. And the question everybody was asking back then was, how are we going to cool them?
We're in trouble right off the bat, gentlemen, if we can't get the vehicle cooled. Right now, we're protecting instruments back here. In a couple of years, it's going to be human beings. And let's face it, men can't take the kind of heat that machinery can. So we've been thinking about some kind of protection for the nose cone, like the refractory oxides, specifically Pyrex glass, quartz, and fused silica. Now, Dr. Gerson, you've done some work in
The idea was conceived coating the nose cone so that some of it would melt off and the rest of the vehicle would be protected. Well, I looked at some of the films in which they took a plastic model, swung an arc jet, which is a high-temperature heat source, in front of it, and you see this thing melt away in a beautiful streamlined fashion. And they thought that they had found the way to cool these re-entry vehicles. I thought deceleration had been overlooked in the early work. If it were important, then the melt would push forward and change the shape and the flow patterns.
Dr. Ostrach.
It may well be that these materials will provide the proper thermal protection, but I think the effect of the vehicle's deceleration through the atmosphere is being overlooked. This deceleration might well oppose the backward flow of the melt and cause it to accumulate at some point on a body like this.
A re-entering body becomes hotter as friction grows between it and the increasingly denser atmosphere. Ostrach predicts that a melting protective covering will move back along the body in concentric ring waves until deceleration causes the body to slow abruptly. Then, he theorizes, the melting material will slump forward, like the occupants of an automobile that comes to a sudden stop. Then the ring waves will project from the sides of the body, cause it to become aerodynamically unstable, and create a tumbling motion that would expose unprotected surfaces to dangerous heating.
And I said, furthermore, I'll prove this to you, because I'll take this simple problem, and in about 4 or 5 weeks, I'll illustrate to you the influence of the deceleration force. Well, as I got into the problem, it turned out that even the simplest aspect was very difficult, and it took me nearly 3.5 years.
Dudley McConnell, like many young men in the aerospace field, is a veteran of this nation's crash program of rocket development.
I started working with NASA on October 1st, 1957. On October 5th, 1957, we heard that the Russians had put up the first Sputnik. All of a sudden, what was thought to be 15 to 20 years ahead of its time was the current state of the art.
McConnell is a long way from home. He grew up in Brooklyn, graduated from the tuition-free City College of New York. How does a young man find his way into the space program?
My father emigrated here in 1919 from the West Indies. It was always assumed that I'd go to college. It was always when you go to college or when you finish college. I was fortunate in never having any doors closed in my face. I was never told, you can't do that because you're black. Simon Ostrach was friendly, extroverted, and had many interesting ideas and outlooks on many situations. He's not the kind that says, this is what you'll do. He puts you on your own, and if you come back with some cockeyed idea, he'll point it out and make a critical evaluation, but he won't tell you what to do.
The teacher and the student, a working partnership that tonight has provided a new group of answers that will help to solve tough space-age problems. For Dudley McConnell, some of the pressure now relaxes. His doctoral degree is in sight. For Simon Ostrach, too, there is pleasure in these moments. Years ago, he predicted that a certain phenomena would occur under certain conditions. Tonight, in the laboratory, he saw that what his theory said would happen did happen. A scientist is permitted these moments of pleasure only after he has earned them. Like the majority of respected scientists, Simon Ostrach has earned his moments of satisfaction through years of determined effort. His parents came to America after fleeing Russia in the early 1900s. He grew up in Providence, Rhode Island.
I was always a small guy. The athletic uniforms in high school were usually too big for me. But in wrestling, I could go against guys my own size. And so I worked very hard at it. And I think it helped me enormously because it made me sure of myself. And thereby I think I became a better person.
Hey, Charlie. You going down the street with me this year? I don't know. You gonna go this year?
I like to referee because it keeps me young and it gives me a chance to be close to young people. For me, it's the closest thing to competing.
Hi, Don. Hi, Doc. Say, I forgot to ask you last week. Are you going to be working the championships this year?
I think so.
How do you think Notre Dame will do?
I don't know, Don. I haven't seen him yet.
Well, I'll see you upstairs.
Okay.
I take it very seriously. I know the rule book inside out and backwards, but I always reread the rules before each match. I feel it's criminal if an official doesn't know the rules. I've refereed other sports. They're fun. But in wrestling, it's the kind of sport where you've got to make a hairline decision and announce it to everybody. One bad call can cost the kid about. You hate to do that.
Si, I think, when he walks in, still mentally pinches himself. Oh, he had such a hard domestic life, and it was such a hard way for him to get an education. I look at those kids now, and they don't know how they're blessed. They just don't know. I hope they never have to.
Everybody asleep?
No, I think Stephanie's still awake.
I'll be in a minute.
Hey,
Hi. Who won it?
Euclid by 3 points. How about driving me to the airport tomorrow?
Sure.
Okay. Good night.
Night.
My father was a very severe man. He was sort of the European type. What he said around the house went. No matter what you did, it was practically impossible to get him to change his mind about anything. You could cry for a whole weekend, but it wouldn't faze him a bit. My kids don't consider that I'm their pal or someone who must entertain them all the time. But on the other hand, they know I'm approachable, they know I'm human. I'm interested in what they're thinking, what they're feeling. They come to me with problems. They come to me with joys. My children know when I'm pleased with them, and they know when I'm getting satisfaction out of what they're doing. And I think it's healthier for them, and it's certainly healthier for me. Well, I've worked the high school district wrestling championship and seen a boy who was ahead try to win big, make a mistake, get caught and lose. And then his coach got up in front of packed stands and threw his jacket at him and yelled, "You dummy." What kind of impression can this make on a boy's life? He gave it everything he had, and he lost. But in a way, I think this is representative of American standards. To be first, under any circumstances, is great. To be second is terrible. I don't really think there's anything wrong with teenagers' values. It's the adults' values that they're emulating.
For several years, Simon Ostrach has been chairman of religious education for Park Synagogue, the largest conservative Jewish congregation in the United States. Under his direction, there have been substantial additions to the program. Ostrach himself teaches high school courses.
Kids often ask me, why do I come down to try and teach them about religion? They say, you're a scientist. Why are you involved in religion at all? Well, I'm always glad when they ask me that because I think I've got some answers for them. First of all, they all think that science is all proven facts and religion's all blind faith. As a matter of fact, of course, neither of these suppositions is true. I try to tell them that moral and ethical law is as much a part of the universe as are the physical laws. You have really a tough time getting them to accept it, but I think it's important that they start to think about it. Perhaps some of them do begin to understand it. And I think if religious education is not capable of meeting these kids at the same intellectual level as their secular studies, is doomed to failure. Just a waste of time. You might just as well forget it.
Good morning. May I have your ticket, please? Welcome aboard, Dr. Ostrach.
Today, Simon Ostrach flies to the California Institute of Technology in Pasadena. He carries a report on the experiment just completed by Dudley McConnell. He will present this report at a seminar lecture before faculty members and graduate students.
There's an interesting piece of work which presented some new and unusual results. I was very eager to present these before a capable audience. I was pretty darn sure it was correct. When you go to a place like Caltech, there are many people there with international reputations, and some of them are working in the same field that you are. When you're speaking to people like this, you can't be foolish. They can and will get up and criticize your work. And in a way, it's kind of scary. It's the kind of sport where you've got to make a hairline decision and announce it immediately to everybody. One of the frightening things about our business, no matter how many successes you've had in the past, the next thing you attempt could be a failure.
It is my pleasure to introduce Dr. Simon Ostrach from Case Institute of Technology in Cleveland. His paper is titled Melting Decelerating Bodies. Dr. Ostrach.
Thank you. Some of you know this project has a history. It is also kind of interesting how we perform this experiment. I got a hold of some material on tektites a couple of years ago.
This is a tektite, a silica meteor that started its plunge as a sphere, but as it melted, formed this flange around its edge. The front or forebody shows concentric ring waves, frozen forever in place when the tiny piece of glass cooled and dropped to Earth. Was it deceleration that caused the melting silica to form these waves? Ostrach and McConnell believe it was. Their theoretical work now seems to interlock with the natural phenomena of tektite formation.
One of the toughest things to get across to people, and in fact to many engineers and scientists, is that theory is not hypothesis, not unreality. But if you do a good, careful theory, it should be pretty close to reality.
For the manned space program, scientists chose sublimating heat shields, shields that don't melt, but go directly from a solid to a gas. However, Ostrach and McConnell continue to develop their theories of melting ablation.
The point is that better, even more general theories than mine will have to be developed to account for these things. If you account for things in advance, you'll never have any trouble.
Version 7, we are recommending that you leave the retro package on through the entire re-entry. This also means that you will have to manually retract the scope. Do you read?
This is Friendship 7. What is the reason for this? Do you have any reason, over?
Not at this time. This is the judgment of Cape Flight.
Roger. This is Friendship 7, going to re-entry attitude then in that case. Go ahead, Cape. You're going out. Okay, Friendship 7, over. This is Friendship 7. I think the pack just let go. Friendship 7, a real fireball outside. Okay, Friendship 7, do you receive, over? Okay, Friendship 7, do you receive, over?
as most of you probably know, the ground telemetry receivers had picked up an impulse that we possibly had a loose heat shield. And for that reason, it was deemed advisable to keep the retro package in place during re-entry so that it would go ahead and burn off, but by that time we would be in a high enough aerodynamic force field to keep the heat shield in place in case it was in fact loose. So there were some moments of doubt there as to whether the heat shield had been damaged and whether it might be tearing up itself. And this could have been a bad day all the way around if that had been the case.
You just don't go along and trust to luck that things are going to work out. In early generation work, you can be crude. But as the demands of technology become more severe, you have to rely less and less on safety factors and more on understanding. For the experiments, we decided to use a vertical wind tunnel in which we suspended a frozen tar ball, and we had an upward vertical...
Ostrach is now describing the experimental phase of the project. The experiment is not conducted to see if the theory is true, but how true it is. Ostrach and McConnell have made certain assumptions. The experiment will tell them how good their assumptions were. To perform the experiment, it was essential to duplicate in the laboratory the conditions a nose cone would encounter in the upper atmosphere. How to make a small model in the lab behave like a full-sized nose cone, slamming at supersonic speed into the dense blanket of air that covers the globe. Deceleration. This is the problem that puzzled Ostrach and McConnell for many weeks.
You know, the life of a scientist is a very frustrating and frightening kind of life. I compare it quite often to the life of a composer or any other creative artist. It takes guts to get up every morning and go to the office when you don't know exactly what you're going to do. Sometimes you don't even know that what you're doing is correct. You've got to wrestle with these things, and no matter how many successes you've had in the past, and no matter how big a reputation you have, the next problem you tackle, you start really like from scratch. And it's you against the problem. And this is frustrating, it's nerve-wracking, and it's frightening. But despite all this, if you get a scientist talking about the work he's doing currently, you can see his eyes light up, and there's a certain excitement.
Good morning. Good morning.
I think the primary characteristic is a fierce pride that the really creative, really good people have. And when they're doing it, they tend to feel that what I'm doing, no one else has done, and I'm doing it completely on my own.
How's it going? I think this is it.
I'll come back later.
No, come here and take a look at this. Here's the tunnel. We suspend a bowl of tar right here. At the temperatures we're going to use, this tar will behave a lot like a heat shield at about 10,000 degrees. Now, the important thing is to simulate the deceleration forces, right? These are the gases flowing up past the body. Here's the pull of gravity in the opposite direction, just like deceleration would act on a nose cone. We calculate how much velocity here will produce how much deceleration effect here.
So if you cut back the velocity here, then the melting portion of the tar feels as though everything holding it is suddenly let go. It's like entering the atmosphere. You think the melt will start waving up about here?
Right.
We had a little aircraft engine supercharger, and really, with a little baling wire and tin, we put this vertical wind tunnel together. My career has always been making the best with what you have. You don't just sit around and bawl because things aren't optimum. You just go ahead and you try and get the job done in the best way that you can. First, what happens is that the heat starts being transferred to the lower temperature sphere. And then, as the material gets warmer and warmer, its viscosity goes down. And out near the layer where it's hottest, the viscosity becomes lowest. And then the wind forces, the pressure forces, and the shear forces take this liquid film and start to move it back. When you lower the velocity of the tunnel, the gravitational force, which is acting like the deceleration force, tends to hold the wave back. Dudley was over in the lab doing the experiments. Suddenly the phone in my office rang, and it was Dudley shouting, "We've done it, we've done it. We've got ring waves, and it looks just like tektites." And I said to him, "Dudley, why are you so excited? After all, the theory predicted it. Don't you believe the theory?"
How much did it cost you to put together that vertical tunnel, Si?
This was a top-level job, about $3,000. But NASA's coming up with $30,000 to build a high-speed centrifuge. And I suspect that we'll do much more sophisticated stuff on that.
Dr. Ostrach, your theory predicts a single wave, yet we know by looking at tektites that multiple waves occur. Why is this?
It's a very good question, Dr. Brodke. In formulating the theory, we assumed that the flow of gases around the body would be a constant. Now, in reality, as the body melts and changes shape, this flow also changes. Now, a more realistic treatment of this would account for these changes in the flow. Then, the multiple waves would show up in the theory. I've got a very bright kid from Formosa, Marty Chen, who's working on that right now.
Dr. Ostrach, I wonder if you'd mind going into the mathematics of that reciprocal Froude number a little more. I think we've got some problems. What you doing?
For me, science is the fact that you know in your own head that you're thinking of things nobody else has thought of. You're solving things nobody else has solved.